Line coverage is the coverage of linear features in an environment. The linear features are modeled as one-dimensional segments or curves. The task is to find routes for a team of robots for efficient coverage of the linear environment features. Since mobile robots are limited by resources such as battery life, we incorporate resource constraints into the formulation. Power lines form such a linear infrastructure. They require inspection for maintenance of lines and detection of vegetation encroachment. Road networks also form linear infrastructure. Line coverage can aid in mapping and inspection of road networks. Rapid inspection becomes especially important after natural disasters to ensure access to emergency services. We model line coverage as a graph problem. We are given a depot which corresponds to the start and end location for the routes of the robots. The linear features to be inspected form the required edges. There are non-required edges that can be used for faster travel between vertices, and the endpoints of all the edges form the vertices in the graph. There are two modes of travel for the robots. The first mode is servicing, wherein task-specific actions such as taking images are performed along required edges. There is a cost of servicing, for example travel time. We also have demand on resources such as battery life. The second mode of travel is deadheading, which corresponds to travel from one vertex to another without performing servicing tasks. There is a cost and a demand associated with deadheading. Both required and non-required edges can be used for deadheading. For ground robots operating in an uneven terrain, the cost and the demand for traveling uphill can differ from traveling downhill. Similarly, for UAVs, costs and demands can depend on the direction of travel due to wind conditions. Hence, we allow costs and demands to be asymmetric. We can now define the line coverage problem. Find a set of routes for a team of robots such that the total cost of the routes is minimized. All the required edges are serviced, the routes are connected to the depot, and the total demand is less than the robot capacity. There are several practical benefits of using the formulation. We ensure efficient coverage of required features by optimizing the total cost of the routes. Only the relevant features are covered, and the formulation can handle multiple robots, capacity or resource constraints, and asymmetric costs and demands. We first develop an integer linear programming formulation. The objective is to minimize the total cost for all the routes. The ILP ensures each required edge is serviced exactly once. The formulation comprises capacity and routing constraints for each robot. The ILP gives optimal solutions when a feasible solution exists. The line coverage problem is NP hard, and solving the ILP formulation to optimality can take a long time. This is not suitable for robotics applications that require rapid solutions. Hence, we developed the Merge-Embed-Merge heuristic algorithm, which has a polynomial time complexity and computes solutions within seconds. Let's look at the Merge-Embed-Merge algorithm. We take a required edge and build a route. The route starts from the depot vertex V0, deadheads to one of the vertices of the required edge, services the required edge, and deadheads back to the depot. Since the costs are asymmetric, both directions of servicing are considered. The algorithm creates a route for each required edge in the graph in the initialization step. We record the route demands at the bottom. Next, we look at the saving in the cost if we merge two routes to form a new route. As merging two routes reduces the amount of deadheading to and from the depot, the total cost of the routes can potentially decrease. There are 8 different permutations to merge two routes, as the costs are asymmetric. The algorithm selects the permutation that gives the maximum saving, provided the resource constraint is satisfied. The algorithm considers each pair of routes, computes the saving in cost for each pair, and stores these savings in the max heap data structure shown on the right. Next, the element with the maximum saving is extracted from the max heap. A new merge tour is formed, shown here in pink. The constituent routes are set to null and won't be considered in future iterations. We now perform the embed step for the newly merged route. We compute the savings obtained if the pink route is merged with existing routes. These new savings are then stored in the max heap data structure. The merge and the embed steps are performed iteratively. Now, the maximum element is extracted from the heap once more. A new route shown in light green is generated. Now we come back to the embed step. Merging pink and green routes is not feasible as it would exceed the capacity of the robot and violate the resource constraint. Thus, no new element is added to the heap. All elements are extracted from the heap and no new merge is possible. The algorithm terminates. We evaluated the MEM algorithm on a dataset consisting of road networks from the 50 most populous cities in the world. Two of these road networks are shown here. We compare the solutions obtained using the MEM algorithm and the ILP formulation. MEM gives solutions within 7% of the ILP solution for this dataset. The entire procedure consisting of graph processing and the MEM algorithm takes around 2 seconds for the largest road network. The MEM algorithm takes only 0.5 seconds for the largest graph. We now show our first experiment on a road network. On the left is the input road network. In the middle we have line coverage routes. There are two routes distinguished by red and blue colors. The black square is the depot location. The solid lines represent servicing and the dashed lines represent deadheading. We flew a DJI Phantom 4 UAV autonomously along the computed routes. On the right, we have the orthomosaic generated from the images collected. The dots in the figure show the locations where the images were taken. For large graphs, it may not be possible to cover the entire graph from a single depot. Thus, we develop a multi-depot formulation. Here we are given a set of depot locations which can be specified by the user or obtained through clustering. We extended the MEM algorithm to directly integrate multiple depots while generating the routes. The new algorithm initializes and computes savings while considering each depot. The overall complexity now depends on the number of required edges M and the number of depots. We obtained routes for the UNC Charlotte campus road network shown on the left. The generated routes are shown on the right. There are 8 depots and 8 routes were obtained using the MEM algorithm with multiple depots. This animation shows robots following the routes. The solid lines represent servicing while the dashed lines represent deadheading. Note that the robots travel faster when deadheading as they do not perform servicing tasks such as taking images. We autonomously flew a DJI Phantom 4 along the routes. The orthomosaic on the right was generated using the images obtained while servicing the road segments. Now, taking turns can be very expensive for robots, so we incorporate smooth turns between adjacent edges in the graph. The formulation takes into account a maximum deviation from the required edges so that each point on the linear features is covered. We also extend the algorithm for nonholonomic robots by incorporating Dubin's curves along with smooth turns into the algorithm. Here, we show routes computed by the MEM algorithm while incorporating multiple depots and turns for nonholonomic robots. The depots are shown as black squares. Deadheading paths between solid required edges are shown by green lines and curves. These deadheading paths incorporate nonholonomic constraints. The line coverage problem has an interesting application of generating routes for the area coverage problem. We decompose the two-dimensional region into cells and compute an optimal service direction for each cell so that the number of turns is minimized. Next, we generate service tracks for each cell shown as green line segments in the middle figure. Finally, we use the MEM algorithm to generate routes that respect the capacity constraints, consider multiple depots, and incorporate non-holonomic constraints. To summarize, we developed solutions for the line coverage problem with multiple resource constrained robots. We considered two modes of travel, servicing and deadheading. The costs and the demands are distinct and asymmetric. We incorporated resource constraints for the robots to obtain safe routes. We evaluated and validated the algorithms in simulations and experiments and showed that the MEM algorithm rapidly computes high-quality solutions. We extended the algorithm to multiple depots and non-holonomic robots. We further used the line coverage algorithms to generate routes for the area coverage problem.